Okay, ladies and gentlemen, we have our last speaker of the day. Just before he starts, afterwards there is a final speech downstairs in the main auditorium, so please don't go anywhere. We're trying to make sure that both speakers finish at the same time. So our next presenter is a wireless security expert. He's the author of books, I don't know, Booker Prize winner maybe? Backtrack 5 Wireless Penetrate and Testing Beginner's Guide. That's a tongue twister. And the Metasploit Mega Primer. He's the founder of SecurityTube.net and is a recurring speaker at Hacktivity. We've invited him back this year to talk more about advanced Wi-Fi for modulars hacking after last year's success. So please give your full attention to Vivek Ramachandran.
Thank you. Thank you everyone for coming. This is the last talk, so hopefully we can probably do 5-10 minutes more because we've lost a little bit of time. My name is Vivek, and today's topic which I want to present is cracking WPA, WPA2 personal and enterprise, both of them. Before I begin, this is the customary shameless self-promotion. I am an electronics and communications engineer, moved on, specialized in security, started my career working for Cisco as a programmer in the layer 2 security team. Most of the .1x and PortSec you see on Cat6Ks is coded by me. Moved on, worked for a couple of startups as system architects, then finally started security research. The first talk which I gave was at DEF CON 15, broke web cloaking, which was an encryption schema now owned by Motorola. Moved on, discovered the first attack, Cafe Latte, which was more of AP-less web cracking. After that, won the Security Shootout India, started my own training company, and last year in Hacktivity, I spoke about Wi-Fi malware. I also run SecurityTube. We have some online certifications now taken by students from 65 countries. And the last shameless slide is Backtrack 5 Wi-Fi pen testing. I'll be giving this book away. I'll be asking a bunch of questions. Whoever can answer gets the book, right? Okay, so what's the agenda? I really want to talk about WPA, WPA2 cracking personal and enterprise. Now, what I've seen is when I interact with pen testers and even companies, most of them have not yet grown beyond web, right? When people say Wi-Fi cracking, most people just talk about web cracking. While WPA, enterprise and personal has a ton of stuff which has happened over the past 3 to 4 years. So to understand WPA, let's look at where we left off, right? Web was all broken. A lot of cryptographic attacks were discovered. You had FMS, which was the very first paper which came out. Then you had Corec, Adrius, PTW, and basically what happened is web was broken beyond repair, right? If you have a web network, whether you use a 64-bit or a 128-bit key, regardless of how complex, your web is going to be broken. Now this is where the IEEE committee said we need a replacement. Now they really did not have much time. So they said, okay, let's come out with WPA, which is going to be an intermediate solution, right? A quick patch. The key thing with WPA is that it has to be compatible with the same hardware which was running web, right? All one could use was a firmware update. And hence, WPA had to be basically based on web. And that is what TKIP is, right? TKIP wraps around web and cleanses many of the vulnerabilities like fast rekeying and things like that. However, the whole alliance also started working on WPA2, which was the long-term solution called the 11i standard. Now, WPA2 was to be based on CCMP, which is based on AES, unbroken at this point. And for WPA2, hardware changes are mandatory. Now, when you look at both, each of these has a personal and enterprise edition. The personal edition is what we all call PSK, right? Pre-shared key, which we use in our homes. And enterprise is what uses .1x in radius. Now, what's the key difference? The WPA standard 11i probably runs into a couple of hundred pages. So I've abstracted all that out, and basically here is the key difference. In web, we use static keys for encryption on both sides, right? Symmetric encryption. In the case of WPA, we no longer use static session keys. The whole idea is to first dynamically generate the key on a per session basis, use it for that session, throw them away. The next time you again connect, create a different key. Right? So first let's look at WPA, WPA2, PSK or personal. Now how does this work? Very simply, you as a user enter a passphrase between 8 to 63 characters. That goes through a function called the PBKDF2 or the password based key derivation function. Right? As you can see, you have a variable length passphrase and you want to map that to a fixed key size which you can use. And this is what PBKDF2 does. The output of that function is a 256-bit pre-shared key. This is what your laptop or mobile clients use. On the other side, the exact same thing happens. The only difference is the administrator is the one who does that. Now, a little bit into the PBKDF2 so that we understand how the cracking process works. This is actually a generic RFC which can apply to any scheme which uses a passphrase and wants to end up with a key. In the specific case of PSK, we use the passphrase, the SSID length, iterate using the PBKDF2 4096 times and come out with a 256-bit key. Right? The 4096 is extremely important because this is what is going to become the bottleneck when we try to crack WPA. Okay, just wanted to give you a little bit of breakdown of how we crack WPA. In web, what did we do? We tried to collect a large number of data packets, right? Once you have a large number of data packets, bunch of them would have the weak IVs. We run it through our algorithms or aircrack-ng, get the key. In the case of WPA, PSK, you really do not require data packets. To crack WPA, what you require is what is called the four-way handshake. Now, what is this handshake before we get into the nitty-gritty details? I said in WPA, we dynamically generate the keys, right? Which means there is an initial exchange. This four-way handshake is that initial exchange, right? So, in WPA parlance, you call the client a supplicant and you call the AP an authenticator. Both of them have the pre-shared key based on the passphrase which you just entered. The first packet goes from the AP to the supplicant, and for all practical purposes of knowing how this works, what we need to remember is this contains a long random value called A nonce. That's it. The second message, before it's sent, the client actually pre-computes the shared key. What all does the client use? The client uses the A nonce sent by the access point. The client generates its own random value called S nonce, uses the MAC address of the access point, its own MAC address, along with the pre-shared key both of them have already generated, and computes the PTK. Now, the client has the PTK. Does the AP have it? No, right? What is missing with the AP to generate the PTK? Just the S nonce, the random value the client created, right? And don't worry if you're a little lost. I'll come back to this and actually show you the packet trace. Once both parties generate the pre-shared key, they need to tell each other, right? It's like you have a key, I have a key. We really don't know if it's the same key. The last two messages is basically key installation, where the AP says, hey, I have the key, and this is the right one. How does it figure that out? In message 2, there is actually an MIC or Michael integrity check. Very high level, it's just a signature algorithm, right? So The client signs message 2 with the MIC. The AP verifies if the signature is correct. If it is, it knows both parties have the same key. Message 4 is the client telling the AP that, hey, everything's fine, let's go ahead and use this key. Now, how does a handshake look like, right? D-Link is my access point, and Apple whatever is actually the client, which is my iPhone, and you have 4 messages. In message 1, I said the key component is A nonce, the long random value. So I have message 1 selected. Here is your A nonce. Right? Message 2 was the client generating its own long random value with a signature over the message. So if we select message 2, you have the S nonce, and if you kind of scroll down here, you have the MIC, which is kind of like a signature over the whole frame, right? And then message 3 and 4, well, this is more of the key installation message. It says install set, install the key, and the final one is the acknowledgement. Now, I wanted to point out something interesting which dictates how WPA is cracked. If you look at message 1, just for a quick second, try and remember this value. Right, you can't. Just the first 3 bytes. Right, 40B3. If you look at message 3, this exactly has the same value as well. This is WPA's way of actually managing the session, right? Think of this as the TCP sequence number and acknowledgement number. Basically, when packet 1 and 3 have the same value of A nonce, what that means is this is part of the same handshake, right? Similarly, packet 2 and 4, which is packet 2, you have the value ACF15, and packet 4 are actually going to have the same value, right? Just keep this in mind. This is where it's going to get interesting later. Okay. Now, at a high level, this is how WPA works, right? You have a passphrase, goes through a function, generates a key. We use these 4 parameters, S nonce, A nonce, AP MAC, and client MAC. Now, let's say you're a hacker who's sniffing the air. You've managed to capture a handshake. Can you get the A nonce out of it? Yes. The S nonce, AP MAC, plain text, client MAC. What's the only thing you don't know in this picture? The passphrase, right? And this is where, using all these parameters in the 4-way handshake, WPA PSK is actually susceptible to a dictionary-based attack, right? How does this work? The hacker is going to have a long dictionary, and we'll actually come to how the cloud and all of that can be leveraged as well. He's going to pick out one of the words, a passphrase between 8 to 63. He generates a pre-shared key, and then he uses a handshake which he has captured over there. Now, how does he verify that the PTK he has derived is the right one? How would he know? Anyone? MIC, fantastic. So using the MIC, right, he's going to use the pre-shared key he just created, all these parameters from the handshake, and check if the MIC value matches, because MIC is just the signature. If the keys match, the value of the signature over the same frame is going to match, right? Let's look at a quick demo of how this looks like. Now I have, I think, 9 demos, and I typically do this as a 6-hour workshop, so so I'm running against time. So what I've done is I'm using PCAP files. I'll show you later where you can pick up all the tools and everything required to do this yourself, right? It's 12 hours of free videos which I have. Okay, so I've shown you the 4-way handshake. This PCAP file contains the 4-way handshake. Now, what we said we really require is actually a word list. So let's go ahead and use the default word list on backtrack. Anyone? Location? Location? Okay, .code, and then you have WPA cracking, right? Now, what AirCrackNG basically does is exactly what we just spoke about. It's going to take the handshake, extract those parameters, pick up individual passphrases in dark code, ensure that passphrase is between 8 to 63, right? Everything else is discarded, and then starts cracking the key. Right? How many keys per second are we doing? On the right hand side? 700, right? It's a little VM where we are using. Now again, in the 6-hour workshop, I would probably allow this to run for half an hour and keep talking. So the passphrase which I've picked up is almost last in dark code. And dark code has 1.7 million words in it. Keep that in mind, because we'll look at how to speed it up a little later. Now, just so you know it works, right? Here is a beautifully crafted list just for this demo. Right? And we go back here, feed this list. There it is. Right? Practically in milliseconds. Key thing, though, remember, WPA cracking is not deterministic, which means if you don't have the passphrase in the word list, it's not going to work. Unlike WEP, where regardless of the passphrase, it would work. Now let's try and look at how we can speed things up, right? How many keys were we doing? 700 keys a second. How much time do you think it would take to go through 1 million keys? 1 billion word lists, words in a list? Right? Not practical. This is where what you want is to speed things up, right? Now, if you look at this entire computation, the bottleneck is just PBK-DF2, right? Why is that? Because PBK-DF2, if you think about it, is a hashing function which is going to do 4096 iterations per word you want to try, per key. Right? Imagine, which means if you talk about 1 billion words, you're doing 4096 billion iterations. Right? Doesn't help when you're in the field. This is where what people do here, is hackers around the world, is something called time memory trade-off. Now the whole idea is, what if we could pre-compute all of these PMKs for a given SSID? If we do that, with a huge infrastructure at our disposal like the cloud, then when we have a handshake, all you do is search, right? Take a passphrase, basically, pick up the key, which you already pre-generated, and that's it. Which means it's much, much, much faster. And this is exactly what we do, is we take a dictionary of passphrases, just like dark word, we pick up the given SSID, create the huge list of PMKs and use that. Very, very important, PMKs are SSID dependent, right? So this is not like your rainbow tables which you create once for the whole lifetime. This is going to change per SSID. So when you do a pen test for a medium-sized enterprise, if they decide to do WPA personal, which they shouldn't, right? Then you could just get the SSID, use the cloud and pre-compute. You have multiple platforms at your disposal, graphic cards and whatnot. And if you really want to do this in a distributed way, use Pirate. Let me show you a demo of how this looks like. Now, don't worry about how I generated the PMKs and all of that. In the end, I'll give you a link from where you can pick up the videos for each of the smaller steps. As I said, it would just take me too much time. Now, this little file here is the pre-generated PMKs for the SSID WPA-PSK, right? And I have used the same 1.7 million words in dark code, which means now we have PMKs for the SSID WPA-PSK using the 1.7 million words in dark code. Tell me how the speed changes now. What's the speed now? Right? And I'm using a VM with probably 512 MB of RAM. Now, Pirate allows you to do this much more faster. You can leverage distributed cores and all of that, which is much more better, right? But if you look at it, 13 seconds is what it took me if I pre-generated the PM case. And this is what people do in the field, right? If I had to do it the regular way, at least 40 minutes on the same VM. Okay, now what are hackers doing? They are leveraging the cloud. Can you buy 50 machines with 4 cores in them or 8 cores in them? How much would it cost? Right? And are you a sponsor to the conference? Okay. So this is where you can actually use cluster compute instances on places like Amazon, right? Now, a sample instance is 60 gig of memory, 88 EC2 compute units, right? And basically, you can stack all of them up and distribute the tasks. How much do you think this costs to use for an hour? $100? 500? Okay, it's even lesser. $2.5 an hour. That's it. That's it. Right? Which means if you had, and here's the best thing about time memory trade-off, right? The more instances which can work in parallel, the lesser time it's going to take. That means you can invest $1,000, probably look at 5 billion word lists, and employ 100 such cluster computes at any given time. If you can distribute the job, all you're spending is $200 an hour, and you have practically 8,000 cores, right, and 6,000 gig of memory to get this done. What's your investment? $200, right? Of course, this is something you don't want to use just to crack your neighbor's Wi-Fi. Okay. Now, this is how WPA personal is cracked. However, the question arises, can you crack WPA personal without the access point? I don't have the access point. You probably have a WPA access point at home. Now you're sitting at the airport, right? I want to crack your home APs.
Software IP.
But you don't know the key. You don't know the key, right? As a hacker, I don't know the key, which means I can't create a honeypot for WPA. Okay, this question is for the book. Anyone? Okay. Now, this is where, okay, go ahead.
Well, you cannot create the same access point, but you can capture the four-way handshake, because for that you don't need the key.
Okay,
You can
can
send
I,
a random number.
okay, if you look at the four-way handshake, right, message 3 will only be sent by the client to the AP if the MIC matches. Fair enough?
Yeah.
If we kind of go back here, let's quickly go back. This is an interesting concept. Okay, this is what it is, right? Now, let's say you as the access point, you're the hacker, you set up a honeypot, right? You don't have the key. Can you send message 1 without knowing the key by generating a long random value?
Yeah.
Fair enough. Now the client receives that. By the way, there's no mutual auth at this point. The client just takes it, generates its own S nouns, sends it back to the access point.
And now you're ready.
So it's like at first, the value that you showed is the
Okay.
first in the third packet as it is in the first packet. Right?
Okay, but right now we just have the first and second packet.
And you are done. I mean, you can
Okay.
start cracking, that's it.
Okay, why can we start cracking? Because we already have. You're getting the book, so a little bit more.
We have both random numbers and we have the message integrity code. We
Okay,
can check.
okay, fantastic. Come on, clap. Good. Okay, so going forward, if I kind of bring it back here, right? Let me give you a bit more background before we move into basically what he said, right? Now, to understand AP-less cracking, you need to understand client behavior. When your home laptop, or when your laptop is not at home, not at work, what does it really do? When you connect to a network, all the network settings, passphrases and all of that are actually cached and stored by most operating systems, right? That's why when you come back home from work and you just switch on your laptop, it just automatically connects. And the whole thing about Wi-Fi is even here, right? You may notice it automatically connects to networks. The reason is you want things to be very simple for the user. You don't want to trouble him every time the wireless gets disconnected. And to be honest, if you studied RF patterns, disconnections are very frequent in Wi-Fi, right? Especially if you move, multipath fading, and a bunch of other things as well. Now, these cached credentials, which is the SSID, and depending on if it's a PSK network, probably the PSK passphrase, is used in an interesting way. When the client is all alone, for example here, it's just sending out what are called probe request packets, right? This is the way for the client to search for access points it has previously connected to, right? How many of you are familiar with probe requests? Okay, no problem. So probe request is, hey, is there a T-Mobile here? Is there a security tube here? I connected to you previously. If you are around, say hi so that we can connect, right? That's a probe request. Here is the problem. Probe request gives you a lot of information about the different SSIDs in your computer's mobile's profile. Let me show you how it looks like, right? Again, this is from here, it's videos because it just takes too much time. Okay, don't worry if you haven't seen these tools before. As I said in the end, I'll point you to a tool, to a DVD which has everything. All I'm doing here is using a tool called AeroDump, which is a wireless sniffer, and this is going to give me a snapshot of what is out there, right? The different APs and the different clients. Now, before we see what's there, a client can be in 3 different modes. Mode 1, connected to an AP, right? Mode 2, just roaming, searching around, isolated. Mode 3, okay, mode 1 is connected to the AP. And mode 2 is just roaming, just searching. Mode 3? Sorry? Okay, which comes back to isolated client, which is mode 2. Ad hoc networks, peer-to-peer, right? That is mode 3. Now, once you run AeroDump NG, some of you may already know how the output looks like, so I'll have to just bore you with some details. For people who haven't used the tool before, the top part here is the list of access points and their SSIDs, right? BSSID is nothing but the MAC address of the access point. Is it visible back there? Here, right? BSSID is the MAC address. Down below is what is interesting. All of this are roaming clients, and if you look to the left, it says not associated, right? These clients are, as we just discussed, probing for different SSIDs they've connected to previously. Which are these SSIDs? That's there on the right. So you have Room Links, Phone AP, T-Mobile. Depending on the geography where you are, this may correspond to a lot of hotspots which are around, right? Coffee shops and airports and all of that stuff. Now, we're going to go ahead, right? And this is actually something from a security perspective is very worrisome. Simply because many a times you can even fingerprint the client based on where it's been. Okay. Now let me ask you a question, right? We said isolated clients, which is what we look at, send out these probe requests, right? Is the access point office for which the SSID is being used here, is it an open one? Is it web? Is it WPA? Is it WPA Enterprise? How do you know that? So, which kind of brings us to the question, does the probe request contain the encryption type of the network it is searching for, right? The answer is no, right? Probe request does not contain that, which means as a hacker, when I see all of these probe requests, all I know is probably default was a network he connected to. I do not know if default was open, web, WPA personal, enterprise, or something else, right? This complicates the scenario a little bit. Because coming to your point, if we have to create a honeypot, how do you figure that out, right? Now, how we do that is you could create something called a catch-all honeypot, but conceptually, here is what we do, right? I've just seen a probe request for security tube. What are the different possible security configurations? Open, web, WPA PSK, WPA2 PSK, WPA Enterprise, WPA2 Enterprise, right? You can throw in SKA as well and say, okay, with SKA, right? What I actually do is I create honeypots with all of these security configurations. Now, here's what happens, right? There is an open AP which says security tube. There is a web AP which says security tube. There's a PSK security tube. There's a enterprise which again says security tube. Now, what does the client do? When the client sends the probe request for security tube, all of these APs reply. Right? They say, hey, I'm security tube, I'm open. Right? I'm security tube, I'm web. I'm PSK. Now the client looks into its own configuration and says, hey, I was supposed to connect to a PSK security tube. Right? And it automatically goes ahead and connects to that honeypot. Now what I've done is I've manually created all these 4 honeypots. There's this tool called Airbase NG. If you haven't used it, no problem. As I said, I'll give you a link for where to pick it up. Just conceptually, I create an access point called security tube, ESSID, security tube. Give it channel 1. Give the MAC address of the access point, which is probably all A's. And the interface on which to create, right? The monitor mode interface. Now, I repeat the same thing, and now I create a web-based AP. Now, of course, before that, we need to create a new monitor mode interface. Now, the interesting thing is, people who've done this before, you can create multiple monitor interfaces on the same physical card. If you put them all on the same channel, great. If you put them on different channels, it still works because the card multiplexes between the channels very fast. It's time division multiplexing, right? The card has one radio which can only be on one channel at a given time, right? Okay, so now I create the second access point again on channel 1. You could change the channels, but throughput drops if you do that. Keep that in mind. And it doesn't matter. The client doesn't care if on the same channel there is 4 different security tubes with 4 different configs, right? Don't worry about the error. It still changes the MAC. So, okay. So what I did is W1 is just web-based AP, right? And now I create a PSK, WPA PSK, and the last one would be a WPA2 PSK. And every single time I create a new monitor mode interface. Right? Can I spare you the if config outputs? Okay. The Z option with 2 is, the small z with 2 is actually WPA PSK. Right? So we have again a WPA PSK AP. And then the final one, which is WPA2 PSK. Now, the way I simulate this is right now my phone, my client is off. Right? I just know it corresponds to one security tube. I have no clue which one. After this, I want to monitor and actually see what's basically happening. Right? We're going to go forward a little bit. So I run arrow dump ng. Here's what I do now. I just switch on my phone. In the real world, the roaming client, as you create APs, if it finds the right one, it'll automatically connect. You wouldn't have to create all of them unless you have really bad luck. Right? Only the last one you create corresponds to the security profile. Okay. I go back. And as you can see, all of our 4 access points are created, right? On the top, you have the WPA2 access point, then you have web, then you have open, and then you have just WPA. All of them have the same SSID security tube. All of them happily coexist. Okay. Now we turn on the client. I mean, this is a simulation, but you could go ahead and do it in the real world as well. And the client would connect to the AP corresponding to which it has a security configuration. Keep looking. I predict it'll be this one. Right. Okay. So if you notice, it basically says client connected, associated, the encryption being used is WPA1 or WPA TKIP with SSID security tube, right? So this is the way we move from we do not know anything about the client profile with, okay, the client has a couple of profiles. One is security tube, which basically is a WPA PSK access point. The next step is finally what we were discussing, which is going ahead and actually creating the honeypot and cracking the key. Okay, conceptually, how does this work? As a hacker, your honeypot does not have the pre-shared key, right? You do not know the pre-shared key. So when the client has connected to you, all you do is send message 1 containing the announce. That's it. Long random value. You don't need the key to create message 1. The client has no way to authenticate you as the real AP because there is no mutual auth at this point. Client sends you message 2 with the MIC in it. Do you have the key right now to validate the MIC? No. Which means you basically drop the connection. Right? You could de-auth the client or you could just disappear. But what has the hacker got right now? Does he have the A nouns? Yes, he generated it. Does he have the S nouns from the client? Yes. Does he have the AP MAC, his own MAC, honeypot? Yes. The client MAC? Yes. What have we basically done? We've actually gone back to this scenario. Right? Now, the hacker has the S nouns, A nouns, AP MAC, client MAC, and he's basically going to do just the old dictionary attack. So AP-less WPA cracking is actually quite simple. The funny thing is I have not seen this mentioned in most places. Right? Nobody mentions this. A lot of people talk about AP-less web cracking. Nobody talks about AP-less WPA cracking. Let me show you a very quick demo. And the demo is basically we creating an access point. Let me explain. Assuming no AP is like the SSID, which the client was querying for, all we do is we create a WPA2 PSK access point. Client connects, we send message 1, client sends message 2, disconnect. We have the handshake. After that, you've already seen what we can do, right? So I run arrow dump just so we monitor what's happening. And arrow dump monitors the fake AP which we are about to create. And it says, okay, the AP is up. Now the roaming client connects to us. And when that happens, keep looking at the top right. Right? As soon as the client connects, AP sends the packet with A nouns, client responds with S nouns, disconnect. Did you see WPA handshake? That's it. Now you have the handshake for the network which doesn't even exist there. Right? And now all you need is 2 packets, message 1 and message 2, containing the A nouns, the S nouns, and the MIC. MIC is in message 2, right? With that, it's just the same process which we did before. Now, a quick word of caution. AirCrackNG and many of these tools seem to fail unless you actually manually pick up those packets and separate them. Because there seem to be a lot of retry which is going on, and AirCrackNG just fails. Right? So keep that in mind, because if you look here, you'll see 2 of 4, 1 of 4, 1 of 4, again 2 of 4, right? AirCrackNG gets confused. The way to do that is just mark the packets, export them as message 1 and message 2, and run what you've been doing before. Let me go back. Okay, so this is how AP-less WPA cracking happens. Now, let me ask you a simple question. Let's say we choose a very long and random passphrase, right? You're an SMB and this is a question I get asked always. We are just a 20-person company. We don't have the finances to have a full-time admin who can run WPA Enterprise with a Radius server, right? Can I please use a very long random passphrase, change it every day? That's my headache. I'll change it every day, right? I'm a 20-person company. I'll do it. I'll go manually and do it. Is WPA Personal safe for use for an SMB which does this? So let's assume, for the sake of simplicity, that a hacker can't crack it. Right? Let's just assume. Is it safe for use in an SMB? Anyone? Okay, here's a quick question. Let's say you are the CEO of the company and I work for you, right? Would you be comfortable in me seeing what you send over the air?
Probably not.
Right? WPA Personal, here is the problem. I have the same passphrase, which means if I can capture his handshake, I can figure out the session key, which means I can decrypt everybody else's session on the same network, right? Which basically means if you use WPA Personal in the enterprise, even in a small SMB, you have to know that you're taking a risk that any employee using the wireless network can decrypt everybody else's traffic. Right? So basically WPA, WPA2 Personal allows for insider attacks. And actually there's a reason why they called it personal. Right? It was for personal use. Okay. Now, I'd just like to discuss an interesting vulnerability, more from a quick theory perspective. There was an interesting hole which was discovered called hole 196. Now, I just told you part of the story, right? When a client connects to an AP, there are actually two different keys. One is the session key just for the client and the AP. The other is for group communication. Now, why do you need a group communication key? Think about broadcast traffic. If every client and AP pair had a different encryption key, the AP would actually have to unicast all broadcast traffic, right? I'd have to send to you with your key, and so on and so forth. Doesn't make sense. This is where WPA and WPA2 have something called GTK, or the group transient key. Now the GTK is common for everybody, right? Which means all of us share the same GTK. And GTK is only supposed to be used for broadcast and multicast. Now, how can an insider abuse the GTK? Basically, an insider could send packets spoofing the origin to be the access point, right? And this actually opens up for things like ARP-based spoofing, right? Simple MITM attacks and things like that. The other interesting thing he can do is actually DOS. By the way, this vulnerability is not patched right now, okay? And most of the people who are using this is all private code, which means you can go back, you can write your own and use it. In every given pen test on WPA, personal and enterprise, this would work, right? What the insider can actually do is he can go ahead and break the replay counter. What is the replay counter? In WEP, if you remember and you cracked WEP, you could replay the same packet and get hundreds more, right? So WPA came out with something called a replay counter and said, okay, if you send this packet in the last 1 minute, there's no way I'm going to accept this packet. How does it do that? Every packet has a replay counter in it. Simple way of functionality, the replay counter keeps incrementing. If the value is 1001, and if the next packet has 990, discarded. The packet is discarded. Okay? Happens a couple of times, an error message is sent. Now, here is what a malicious insider with hole 196 can do. He can send a packet updating the replay counter to a much larger value. What happens now when the legitimate AP or the client, depending on which direction he sends the packet, sends its next packet, the replay counter is already updated to the larger value. Right? In the beginning, the AP silently discards all the packets, so will the client. couple of errors, they send an error message, again connection needs to be reinstated. This can happen network wide. Right? Okay. Now, WPS is related to personal. So what really happened with WPS, right? This was a very easy way for devices which did not have elaborate keyboards and things like that to download network configuration and quickly be on the internet over Wi-Fi, right? Here's what the problem with WPS. When they released it, they wanted it to be very, very easy to use. So the WPS pin code is actually behind almost all network devices which support it. All the access points which you use with WPS, turn it around, there'll be a WPS pin, right? It doesn't end there. This pin was actually supposed to be random. Many manufacturers actually kept part of the pin static and only started changing the remaining bytes, just like a MAC address, right? If I'm Apple, first 3 bytes is reserved for me, change the rest. What this allowed hackers to do is run a brute force attack against WPS. Here's the whole idea. We start guessing the pin. WPS has a small vulnerability where when you guess the wrong pin, it can actually tell you whether the mistake was there in the first half or not. That actually aids you to zero down faster, right? Now, one of the other things which vendors were supposed to do is they were supposed to time out on brute force attacks, which is if I send 5 packets trying to guess the pin, they don't allow me to send any more packets, let's say for the next 5 minutes. Some of the earlier firmwares did not have that, which means you could just bomb them with these packets and brute force the pin, right? The later ones have it, the recent ones hopefully have patched most of this, but it still seems to work for some. How does this look like? So the standard tool to do WPS brute forcing is called Reaver, and all I show here is, hey, you have a WPS access point. Actually, any WPA personal access point just needs to be enabled with WPS. That's it. I mean, there's no separate configuration. With Reaver, all you do is mention the MAC address of the AP which you're attacking, or the BSSID as they say, right? Paste that, Reaver will now brute force the pin. It'll try various combinations, use all of these different mistakes which vendors have done, and tries to zero down on the pin, right? I ran a previous session, that's why the question, or else you wouldn't get it. Now, it tries the pin. There are a bunch of messages, M1, M2, etc. ACK, NACs, don't worry. In the end, basically, if it does not get the pin, you get the NAC, and after that, you basically try for the next pin, right? On an average, depending on if your AP runs an older firmware or a newer one, this can take between half an hour to 16 hours, right? Of course, if everything is done right on the recent firmware, it might even be impossible. Because the real thing which can stop this is just the timeout, right? If you time out the number of attempts a minute, basically you don't allow the attacker to break in at all. So what I've done is just to quickly kind of demonstrate that it works, I use the right pin, right? Of course, if we had all the time, we would again run this for 8 hours, but how would the output look like once you zero down on the pin? You can try this at home if you have an old AP. Old would mean just a year, right? It would work. So the whole idea is once the right pin is given, you can download the configuration, which basically includes the passphrase, and that's what you would see. That's it. So the WPA PSK passphrase is RAM, as an example, right? It's extremely easy to conduct. The tool is very stable, so wouldn't really require anything more than that. Okay, so that's what was wrong with WPS, the brute force attack. Okay, this is something I spoke last year about in Hacktivity, but I'll just spend 3 minutes because this is part of enterprise. It's not fixed. You can go back to your office and do this. How many of you have Windows 7 running in your office? Rest of the guys, XP? Or 8? 8 already? Okay. So, can you, Linux, of course, fair enough. Can you create an access point on Windows? Okay. Great, right? Some of you attended last year's talk or probably already know about it. The funny thing is, on Windows 7 and Server 2008 R2 onwards, you can actually create a WPA2 PSK access point on your client card in a Windows machine. Now you may ask me, hey, does this depend on the specific chipset which my laptop has and all of that, right? Typical to how monitor mode is created? Answer is no. If the laptop or if the external card says it is Windows 7 ready, it has to mandatorily support this feature. There is no option, right? So very quickly, I'll just take 5 minutes because I spoke about this last year. It gets even more interesting. Your card, right, does not need to be a dedicated access point. Your card can be connected to your Office AP, and at the same time, you're allowed to create an access point on the same card. Why is that? Imagine you go to a hotel, you want to connect your iPhone, your iPad, your other laptops and all of that on the hotel network, but they charge you per device. And that's when you use the hosted network, bring it up, just connect the host computer to the AP, all your devices basically tunnel through it using this feature. So the key part here is, with this feature, a Windows computer can use a single physical adapter to connect as a client to a hardware AP, while at the same time acting as a software AP, right? Same time. How do you create a hosted network? So if you want to see the whole detail of the research I did with this, you can look at last year's Hacktivity talk. It's all there on their website. But it's extremely simple, right? Here is all I'm doing. Step 1 is I just connect my computer to a normal access point, right? This can be your Open AP, this could be your Office AP, anything, right? So the connection succeeds, and I'm connected. Now, I'm going to create, so as you see it's connected, I'm going to create an access point on the same card, right? How do I do it? You could actually type along if you want, which is netsh wlan set hosted network, mode is equals allow, ESSID equals whatever ESSID you want to set, and because it's WPA2 PSK, just 2 minutes? Okay. Is that with the 10-minute extra I asked for? Okay, this is going to go fast. Okay. Can I have 5? It's almost done. Okay, so you could create the access point, and this is going to kind of run in the background. The best part is malware can do this, so watch the talk which I had given in the last year. So let me just put this off, and let me actually go to the final part, which is WPA Enterprise, right? So we've seen PSK, we've seen AP-less cracking. Now let's look at Enterprise. Now Enterprise actually gets interesting. You have 3 entities: supplicant, authenticator, which is your AP, which is just a dumb relay to your authentication server, which is there at the background, right? There are multiple mechanisms which you can use for auth, right? In reality, when you talk about WPA Enterprise, you may always hear this term EAP, right? Extensible Authentication Protocol. EAP is just a framework inside which you can tunnel any other auth protocol. Now, Microsoft's version of what they've put on all machines is PEEP. And then you have EAP-TTLS, which is more widely supported. EAP-TLS, which we'll come to, is the most secure and the least deployed, as you probably expect already, right? So PEEP, how does PEEP work? 2 phases. Phase 1 is similar to what you see in SSL, certificate-based connectivity, right? The whole idea is the client goes ahead and creates this encrypted tunnel. Now, what do they send inside the encrypted tunnel? Depends on the inner authentication protocol. In the case of PEEP, it is basically MS-CHAP v2. In the case of things like EAP-TTLS, you have many other options, right? Now, how do you crack PEEP? The problem is, from an encryption perspective, there is no vulnerability. Okay, there's no vulnerability. The only thing we can actually do is somehow get the user's MS-CHAP v2 challenge and response. MS-CHAP v2 is broken, right? How do we do that? We set up a WPA2 enterprise honeypot. Now this honeypot has the same SSID as your enterprise, has a fake certificate. So this attack is similar to your SSL MITM, which means two possibilities. You have a client which does not honor certificates or accepts any certificate, or you have the user explicitly pressing OK, right? So we've set up the honeypot. Let me quickly show you. I'll just take 2 more minutes. We should be done. As I said, 6 hours compressed. So what's happening? Quickly, the background. Okay, now the terminal at the back is where your Radius server is running. Now all of this is running on the attacker's machine. I have a customized version of Radius called Free Radius WPE, right? Wireless Spawnage Edition. Again, free, already installed in Backtrack. It's running, and on this terminal, I'm just viewing the log file for the Radius server. Is Joe here to bounce me off?
I'm not the enforcer. I bring gifts.
Okay, thank you. So, and this is the client. And what I've done is the client is in VirtualBox. It's a Windows 7 machine with an external card, so we can see both the stuff at the same time. And what we've done here is we connect to the access point, and this is misconfigured, which is it accepts certificate. I'll show you what the misconfiguration is. We go ahead, we connect to the network, and anyone who's used PEEP in the enterprise, you know basically you're going to get a username and password quick pop up as soon as you connect to it, right? You fill that up. It says additional info. Most cases, this is the logon credential for your enterprise. Okay? That's an interesting part here, right? So the moment we enter this, well, the hacker does not really correspond to the real network. Connection fails, but look in the background. Because we did the PEEP MITM, we actually got the challenge and response which went through the tunnel. Now in reality, what PEEP was protecting was just this challenge and response by encrypting over it. Which means now what we can do is we can use any of the old dictionary attacks against MS-CHAP v2 and go ahead and run this against it. Kind of move forward a little bit. Right? AS Leap is the one. Originally this was against Leap, which was Cisco's implementation, lightweight EAP. Leap also had MS-CHAP v2 internally. That's why you can use the same program to run the challenge response on it, right? We just copy the challenge response, give a word list. And if it exists, then it cracks the password. Now, why do I feel it's actually much more easier to crack enterprise than personal? Because if you think about it, the MS-CHAP v2 credentials you're cracking is usernames and passwords on a per user basis. So if you can get 10 of them, the surface area is high. If the enterprise does not have a good password policy, much more easier to crack, right? PEEP hacking in one slide: enable validate certificate, enable connect to these servers, you have trusted authorities by default, Thwarte and all of that. Again, protect against the dumb user, which is do not prompt user to authorize, and that's it. Fantastic, right? This is what I see, just a minute. This is what I see in 90% of enterprises, and it's vulnerable, right? And I would love to kind of hear what you guys think, and going to do a Q&A, but we don't have time. Here's the answer. If you do not specifically mention the servers and the names, it does not make any sense, because a hacker could buy a certificate from any of these certifying authorities. Is that a valid certificate? Right? Which means the client would actually accept the certificate without prompting you. And in the real world, when you do that, it's actually much more easy to crack PEEP, because all you have to do is buy a certificate from Thwarte and pen test. right? The funny thing is most people check that. If you don't have anything filled in, it still accepts. It just means any server which has a valid certificate, right? Okay, last two EAPs, TTLS. TTLS is similar to PEEP. It's basically like the open standard. There's no other difference. If you looked at how to crack EAP TTLS, it's exactly the same way, right? Windows only supports PEEP by default. For TTLS, you need third-party clients. The Mac supports EAP TTLS by default. So I use my Mac to connect. And what you would basically see is these have the certificate errors, right? Let me kind of go back here. So if it's misconfigured, all it does is basically says, hey, put in the username and password, and there you go. Now, I was showing the demos with the valid certificate, but I think someone reported, and they revoked the certificate and sent me a notice. So if you want to do a pen test, you could buy a valid certificate and do it, but just ensure you don't tell them that you procured one. So, right? So this is it. There you go. There you go. Okay. So what is the solution? Okay. Before that, you could leverage the cloud. We talked about GPU clusters and all of that. You could create your own. There are sufficient tools out there to do that. But if you don't want to do it, Cloud Cracker allows you to crack WPA, WPA2 personal handshakes, as well as crack MSCHAP v2 credentials, right? In the cloud, and they basically have a service, I think this is 300 billion, right? 300 million, sorry. 300 million words in 20 minutes, $17. And so I don't work for them, so I don't get a cut. Okay, last, if you want to secure peace of mind, EAP TLS, it uses both client and server-side certificates, right? I've seen very, very few enterprises deploy simply because certificate management is a huge pain, right? Regardless of whether you have a local PKI or you try to do it elsewhere. Revoking certificates, and the kind of questions I get asked is, should one user across all devices have the same certificate? Should one user across all devices have different certificates for every device? A lot of deployment-related things which are more difficult to take care, right? So if you haven't done Wi-Fi security before and you want to have a look at that, go to SecurityTube. I've given out 12 hours of free lectures, and when I say it's really free, right? It's nothing charged. You can download all the attacks which we've talked about, how to set up all of that platform right from scratch. Everything's there, right? Thank you guys. No time for question, but I can take it outside. Thank you.